in the blood? Well, we know that most of the oxygen combines with iron atoms within the hemoglobin molecule. Remember, each hemoglobin molecule has 4 globin chains, and within each of those globin chains sits a heme group that contains iron. Okay. Because oxygen can bind to the iron, each hemoglobin molecule can carry 4 molecules of oxygen. Okay. So when hemoglobin is fully saturated with oxygen, we call it oxyhemoglobin. So about 98.5% of our oxygen is carried combined to hemoglobin within the bloodstream. It's bound. About 1.5% of the oxygen carried within the blood is simply dissolved in the plasma. So that's unbound. That's not noted here on the chart. I'm just telling you that. Is that the majority of the oxygen carried is bound to hemoglobin, about 98.5%. Only a small percentage of the oxygen that's being carried by the blood is dissolved, unbound. Now let's talk about the way CO2 is carried. CO2 is carried in 3 different ways. About 7% of the CO2 is simply dissolved in plasma, it's carbon dioxide. About 23% of the CO2 is carried bound to hemoglobin, but it's not carried at the same site. Instead of being bound to the heme group like oxygen, CO2 reacts with the amino groups of the hemoglobin molecules, in which case we call it carbaminohemoglobin when it's carrying CO2. But notice again that the CO2 is bound at a different site within the molecule, not at the same site to which oxygen binds. Okay? So that accounts for 30%. When you include the dissolved CO2 and that's bound to hemoglobin, that accounts for 30% of your CO2. The other 70% of the CO2 reacts with water in the presence of an enzyme, carbonic anhydrase, found within red blood cells. Okay? When it reacts, it forms carbonic acid that then dissociates into water and bicarb. Okay? So think of it this way, the CO2 is going to be carried as bicarb. Now, this reaction occurs inside of red blood cells because that's where most of the carbonic anhydrase is. But once bicarb is formed within the red blood cell, it leaves the red blood cell and is carried within the plasma back to the lungs. Okay. So this is happening at the level of the tissues. CO2 is entering into the bloodstream, it enters into the red blood cell, reacts with water, forms carbonic acid, dissociates the hydrogen bicarb. The bicarb then leaves the red blood cell, enters into the plasma where it's carried back to the lungs. So 70% of CO2 is carried as bicarb ions. Okay, you may have not caught that. This is the reaction. You've seen this reaction before, maybe, or maybe not. Maybe not, but you'll see this reaction a lot in the future. It's a reaction that occurs not only in the lungs, but it occurs in the GI tract, it happens with the brain, it happens all over the place. So this is a graphic depiction of what I just said, is that when CO2, which is building up within cells of our tissues, okay, when it leaves the cell, it's going to enter into tissue capillaries. Some of it is simply going to be dissolved in the plasma, about 7%. Some of it is going to enter into the red blood cell and combine with hemoglobin to form carbaminohemoglobin. And then the majority, 70%, is going to enter into the red blood cell and undergo this reaction, which results in formation of bicarb and hydrogen. That bicarb is then going to leave the red blood cell and it's going to be carried in the plasma back to the lungs. All right, so those are the three methods by which CO2 is carried within the bloodstream. Now, once this process here, by the way, is part of internal respiration. That blood, which is picking up CO2, is going to travel back to the lungs. Okay? And this represents the respiratory membrane within the lungs. When that blood reaches the lungs, that the CO2 that's dissolved is simply going to cross over that respiratory membrane, following its gradient. CO2 is 45 millimeters in the blood, 40, so it's going to cross the membrane. The CO2 that's bound to hemoglobin is going to dissociate, and the CO2 then is going to cross over. What about the bicarb that was being carried in plasma? That's going to cross back into the red blood cell and engage in that same reaction in reverse. Bicarb is going to react with hydrogen, form carbonic acid, dissociating the CO2 in water. So we regenerate the original CO2 that was formed in the tissue, and that CO2 then crosses over. So the opposite occurs during external respiration, and CO2 then crosses over back into the lungs. And of course, when we exhale, and when we take a breath out, whatever CO2 that crossed over is released into the atmosphere. Okay. Last thing I want to say today is about regulation of ventilation. When we talk about the cardiovascular system, we discussed baroreceptors that are present within the carotid sinuses and the aortic arch. At these same sites, within the aortic arch and within the carotid sinuses, you have chemoreceptors. Okay? The chemoreceptors in the carotid sinuses are called carotid bodies. Okay? The chemoreceptors in the aortic arch are called aortic bodies. So what do these chemoreceptors sense? They sense
The chemical exchange?
yeah, chemicals. CO2, and this little subcase, this small case A represents arterial blood. Okay, so partial pressure of oxygen in arterial blood, partial pressure of CO2 in arterial blood, and pH. That's what these chemoreceptors detect. Just like the baroreceptors, these chemoreceptors have afferent connections with the brainstem, with respiratory centers within the brainstem that are located within the medulla oblongata and the pons. That's where the respiratory centers are located, in the medulla oblongata and the pons. Okay. In a very analogous fashion to baroreceptors, afferent fibers from the aortic bodies are carried by the vagus. Afferent fibers from the carotid bodies are carried by the glossopharyngeal nerve. So it's 9 and 10 all over again. Now, let's suppose there is a decrease in PO2 or an increase in CO2 or a drop in pH of blood. Any of these three conditions are going to trigger a respiratory reflex via those carotid bodies. That results in an increase in the rate and depth of ventilation. So if the PO2 drops, the PCO2 goes up, or the pH falls. That's going to trigger the respiratory reflex where we're going to be driven to take deeper and more rapid breaths. Okay. Now, by the way, the opposite conditions. If your PO2 is high, PCO2 is low, and pH is high, the opposite would inhibit that respiratory reflex. The opposite conditions would decrease respiratory rate and decrease depth of ventilation. So this is referred to as the respiratory drive. And of these three triggers for the respiratory drive, do you know which one is the strongest? That plays the biggest role?
The pH.
No.
Oh.
PCO2. That's the major trigger for the respiratory. I'll give you an example. Every summer, my wife and I go to Gulf Shores. We're creatures of habit. Sometimes we go twice. We always stay at this is fun. We always stay at Sea Chase, which is a condominium, a real nice one. And inevitably, by the way, we always see Holy Cross students. Isn't that crazy? It's an exception when we don't see one or more of our students, either during the summer, spring break, whenever it is we go, during winter break. Okay? And then sometimes we'll see people we know from the hospitals. But inevitably, you can't go. A lot of people, I guess the fact is just a lot of people in New Orleans go there. All right, so the first thing I do, sometimes we'll leave a little bit later in the day, so we get there in the evening. But I have the same protocol. Okay, the first thing I have to do, and I may have told you this, is I go down to the pool. I have a nice sized pool. Okay? And just to make sure I still have it, okay, I will jump into the pool at one side and swim underwater all the way to the other side. Okay? And I will not come up before I reach the other side. So far, I've been successful for the past 20 years in doing this. Okay? Now, have any of y'all swum underwater before?
Yeah.
Okay, there you go. So you know. So when you're swimming underwater and you get maybe, 90% of the way there, you're going to feel an urge to take a breath in. You're going to feel that drive kicking in. That's telling you, breathe, breathe. Go up there and take a big old breath. Okay? You have to suppress it. Okay? But that's what that is. That's kicking in. That's urging you to take a breath in. That's the respiratory drive, because as you're swimming underwater, you are hypoventilating.
We had to do that for our drills too.
For
Like
you.
we would do 2 laps without breathing.
Oh, you're just trying to one-up me here. Okay. So, but what's happening is most of us are not breathing while we're underwater. And so the CO2 is climbing because we're not getting rid of it. And so as that CO2 climbs, it triggers that respiratory drive. Now, let me point out one other thing. Within our bloodstream, by the way, I'll come back to that. Within our bloodstream, CO2 can react with water. This doesn't happen as rapidly as within red blood cells, because red blood cells have a lot more carbonic anhydrase. But within our bloodstream, CO2 reacts with water to form carbonic acid that can dissociate to form hydrogen and bicarbonate. Okay? So when we hypoventilate, CO2 climbs. Partial pressure CO2 climbs. That condition, by the way, where CO2 is high, is called hypercapnia. Hypercapnia. Okay. In fact, the normal PCO2 in arterial blood gases is between 35 and 45 millimeters of mercury. We think of the average reading as being then 40 millimeters of mercury. Okay. But it can range from 35 to 45. Anytime the CO2 climbs above 45, we refer to that as hypercapnia. If the CO2 falls below 35, we refer to that condition as hypocapnia. Hypocapnia. And of course, hypercapnia is going to be associated with hypoventilation. In other words, if we underventilate, if our minute ventilation is low, CO2 is going to climb. Hypocapnia tends to be associated with hyperventilation. We're blowing off CO2 at a rate greater than it's being produced. The level falls within our bloodstream. Okay? Now, in the setting of hypercapnia, where we're hypoventilating, that excess CO2 is going to react with water to form carbonic acid, dissociate to form hydrogen and bicarbonate. By the way, this is called, the fact that this equation is an equilibrium, and now we're driving it from left to right. What principle in chemistry is that?
It's either oxidation or it's the other one.
All right, when a substrate on one side of an equation
Oh no, okay.
increases in concentration, and it drives the equation to the opposite side, what do we call that? Le Chatelier's principle? Have you ever heard that?
Oh no.
I have, but I can't pull that off the top.
So when CO2 increases, that's going to cause this reaction to proceed left to right. Okay? And so, as a result of this reaction, the hydrogen ion concentration in the blood is going to climb. When you have an increase in hydrogen ion concentration, that's the direct result of hypercapnia. We call this condition respiratory acidosis. So in respiratory acidosis, the pH is low, but the CO2 is high. The scarecrow. Okay? So with respiratory acidosis, we're hypoventilating. That's driving this equation left to right, causing an increase in hydrogen ion concentration in the blood that drops the pH. We would call that drop in pH an acidosis.
So hypocapnia leads to respiratory acidosis?